Hi, I'm Saurav Agarwal with Srinivas Akella from the Department of Computer Science at the University of North Carolina at Charlotte. Our paper is titled Approximation Algorithms for the Single Robot Line Coverage Problem. We'll first introduce the line coverage problem, then discuss the related work, discuss our approach to solve the problem, and finally conclude our work. Line coverage is coverage of linear environment features. For example, in the figure on the right, we show the UNC Charlotte campus road network, and the road network corresponds to the linear environment features. We model the linear environment features as 1D segments or curves, and the task is to find a tool for a robot for efficient coverage of the linear environment features. Applications include inspection of road networks, power lines, and oil and gas lines. We model the single robot line coverage as a graph problem. We are given an input graph G with edge set E, a set of required edges ER. These required edges correspond to the linear features that are to be inspected. We have non-required edges, and these edges can be used for faster travel between vertices. Finally, we have the vertex at V, and the vertices correspond to the endpoints of all the edges. There are two modes of travel for the robot. The first mode is servicing, wherein task-specific actions, such as taking images, are performed along required edges. There is a cost associated with servicing, for example, travel time. Each required edge needs to be serviced exactly once. The second mode of travel is deadheading, wherein the robot travels from one vertex to another without performing servicing tasks. Both required and non-required edges can be used for deadheading. There is a cost associated with deadheading, and since task-specific actions are not performed during deadheading, the service cost is usually more expensive than the deadheading cost. An edge can be deadheaded several times. For a ground robot, the cost of traveling uphill can be different from cost of traveling downhill. Similarly, for a UAV, cost of traveling against the wind can differ from those of traveling with the wind. Hence, we consider the cost to be asymmetric, and both the servicing and the deadheading cost can be different in the two directions of travel for the edges. Given a graph G with costs for servicing and deadheading, the single robot line coverage problem is to find a tool that minimizes the travel cost such that the tool is connected and all the required edges in the graph are serviced exactly once. There are several practical benefits of using the formulation. The formulation ensures efficient coverage of required edges by optimizing the total cost of tool. Only the relevant features are covered. This reduces the coverage time, amount of sensor data, and the time for analysis of the data. The formulation can handle asymmetric costs, and we consider separate costs for servicing and deadheading. We now discuss the related work. The traveling salesperson problem and the arc routing problems are related to the line coverage problem. We'll also discuss the applications of line coverage in robotics. The traveling salesperson problem, even with triangle inequality, which we denote by delta TSP, is NP hard. Held and Karp gave a dynamic programming algorithm that runs in O of 2 raised to the power of n square computation time, where n is the number of vertices in the graph. Christofides gave a 3x2 approximation algorithm that runs in O of n cube time. However, approximation for general TSP is NP hard. Svensson et al. Very recently gave an approximation algorithm for delta TSP on asymmetric graphs. This approximation factor was further improved by Traub and Weigen to 22 plus epsilon. There are several related outrouting problems. The simplest of these problems is the Chinese postman problem, wherein all the edges are required and the cost for servicing is symmetric in both the directions. The deadheading costs are also same as the servicing costs. This problem can be solved in polynomial time optimally. Next, we have the windy postman problem, wherein the cost for servicing is asymmetric. This problem is, however, NP hard. Raghavachari and Veeraswamy gave a 3 by 2 approximation algorithm for the windy postman problem. Next, we have the rural postman problem. In this problem, the set of required edges can be a subset of the entire edge set. So we have both required and non-required edges in the graph. The cost for servicing is symmetric. This problem is also NP-hard, and Fredrickson gave a 3 by 2 approximation algorithm for the rural postman problem. Next, we have the windy rural postman problem or asymmetric rural postman problem, wherein the cost for servicing is considered to be asymmetric. Van Boven et al. Gave an alpha C plus 3 approximation algorithm for the windy rural postman problem. Over here, C is the number of connected components in the required graph, and alpha C is the approximation factor for delta TSP on asymmetric graphs with C vertices. In this paper, we consider the single robot line coverage problem, wherein the cost for servicing and the cost for deadheading both are considered to be asymmetric. Moreover, we consider the costs for servicing and deadheading to be distinct. This is different from the other standard arc routing problems. We give an alpha C plus 2 approximation algorithm for the single robot line coverage problem. Since the windy rule postman problem is a special case of the single robot line coverage problem we consider in this paper, our approximation algorithm also improves the previously best approximation factor. Easton and Burdick considered rule postman problem with K vehicles, wherein they developed heuristic algorithms for coverage of 2D object boundaries. Shu and Stentz developed online KRPP and developed algorithms for coverage of street networks. Dell and Seng developed algorithms for coverage of road networks with dynamics constrained robots. Ho et al. Developed MLP and approximation algorithms for coverage of road networks using the Chinese postman problem with Dubin's curves. These problems did not consider asymmetric nature of the graphs, and moreover, the servicing and the deadheading cost were considered to be the same. Recently, we developed MLP and heuristic algorithms for line coverage with multiple robots. We also considered resource constraints on the robots, such as battery life, in the formulation. We now discuss our approach to solve the single robot line coverage problem. We developed an LP formulation, and based on this formulation, we developed approximation algorithm in stages. First, we considered graphs with all required edges, with special cases of Eulerian graphs and then general graphs. Next, we considered rural graphs, that is graphs with both required and non-required edges. We break it into two special cases based on the required graph, that is graph induced by required edges. In the figure on the right, the solid blue edges are the required edges, and the dashed green lines are the non-required edges. The required graph has two connected components. We look into required graphs with a single connected component and then required graphs with multiple connected components. We first generate a minimum cost digraph by selecting the service arc direction with minimum cost. For example, in the graph on the top, we have a red edge between vertices I and j. The cost of servicing the edge from I to j is 2, and from j to I is 4. Hence, we select the arc direction from vertex I to vertex j, as shown in the bottom graph. The cost of the minimum cost digraph is the sum of the service costs for all the arcs in the digraph. Next, we introduce a reversal variable RA with a value of either 0 or 2. If RA is 2, then the arc is reversed. So if the reversal variable corresponding to the red arc in the minimum cost digraph is 2, then the new service direction is from j to I. The cost of reversing the direction of an arc is equal to the difference in the cost of servicing in the two directions. We now construct a new network flow digraph from the minimum cost digraph. For each arc, we add 3 arcs in the flow digraph. An arc A for deadheading in the forward direction, an arc A bar for deadheading in the backward direction, and an arc A prime representing the reversal of service direction. The arc A prime is in the opposite direction to that of the arc in the minimum cost digraph. The arcs have a unit flow cost corresponding to the deadheading cost and the service reversal cost. Since an edge can be deadheaded several times, the capacity of the arcs for deadheading is infinite. As the reversal variables can take values at most 2, the capacity for reversal arcs is 2. The cost of the flow is then the unit flow cost times the amount of flow summed over all the arcs in the flow digraph. Lastly, for each vertex V, we assign a flow demand equal to the difference in the out degree and in degree, and this is equal to the imbalance in the graph. We show that for a coverage to tau, there exists an equivalent flow digraph with a corresponding flow such that the cost of the two is equal to the sum of the cost of the minimum cost digraph and the cost of the flow. And also the node flow demand dV is satisfied for each of the vertices. Let dF be the flow digraph with cost, capacities, and node flow demands as discussed. The minimum cost flow problem is to find a feasible flow F such that the cost of the flow is minimized and the demand is satisfied for each of the vertices in V. Orlin gave an algorithm that runs in O of m log n times m plus n log n, or O tilde of m square plus mn. Here m is the number of edges in the graph and n is the number of vertices in the graph. We show that for Eulerian graphs with all required edges, the optimal solution for the minimum cost flow problem gives an optimal and feasible solution for the line coverage problem. The overall running time is dependent on solving the minimum cost flow problem, which can be solved in O tilde of m square plus mn time. Now we look at general graphs wherein all the edges are required but are not necessarily Eulerian. In such cases, the minimum cost digraph may have vertices with odd flow demands, and the optimal flow values need not be even. While it is not an issue for the flow along deadheading arcs to be odd, we need to assign service directions to edges for which the flow through reversal arcs is 1. We resolve this issue by traversing the ambiguous edges twice, once for servicing and the other for deadheading. There are two ways of assigning directions due to cost asymmetry. For example, in the bottom figures, we can first service the edge by traversing from vertex I to vertex J and then deadhead back to vertex I. Alternatively, we can deadhead from vertex I to vertex J and then service the edge in the direction from vertex J to vertex I. We select the service and deadheading directions to minimize the cost. We also short-circuit consecutive deadheadings with shortest cost paths. We show that given a connected graph G, wherein all the edges are required, and cost for servicing and deadheading, the algorithm generates a coverage tool with cost at most twice the cost of the optimal coverage tool. This means that the algorithm is a two-approximation algorithm. The running time is dependent on the solver for minimum cost flow problem, and this can be solved in O tilde of m square plus mn time, where m is the number of edges in the graph and n is the number of vertices. We now discuss the rural graph, wherein we have a set of required edges that can be a subset of the entire edge set, a set of non-required edges that can be used for faster travel between vertices. We'll first consider the case wherein the required graph has a single connected component. For example, in the graph on the right, we have the blue solid lines representing the required edges. The graph induced by the required edges, in this case, is connected and thus has a single connected component. Next, we'll consider required graph with multiple connected components. We'll use the network flow model to solve this problem. Similar to the previous case, we first construct the minimum cost digraph, then we construct the network flow digraph from the minimum cost digraph. For each arc in the min cost digraph, we add 3 arcs in the network flow digraph: a forward deadheading arc, a reverse deadheading arc, and a service reversal arc. For each non-required edge, we add two arcs corresponding to deadheading in the two directions. We assign a unit flow cost for deadheading arcs equal to the deadheading cost, and for the service reversal arc, we assign unit flow cost equal to the service reversal cost. Since the edges can be deadheaded several times, the capacity of the deadheading arcs is infinite, whereas the capacity of the service reversal arc is 2. Finally, for each vertex V in the entire vertex set, we assign the node flow demand equal to the out degree minus in degree in the min cost digraph. We show that given a graph G that can have required edges as a subset of the entire edge set, such that the required graph is connected, the algorithm generates a coverage tool with cost at most twice the cost of the optimal coverage tool. This means that the algorithm is a two approximation algorithm. The running time of the algorithm is O tilde of m square plus mn. Now we look at the case where required graph may have multiple connected components. For example, in the graph on the right, we have the required edges shown in blue, and the graph induced by these required edges have three connected components. The previous algorithm in such cases may lead to a disconnected tool. In order to resolve this, we select an arbitrary vertex for each connected component to form a vertex set V0. Then we create a complete auxiliary graph by adding edges between each pair of vertices. We assign the edge cost equal to the shortest deadheading path costs. Then we compute an asymmetric traveling salesperson tool on the graph G0. We show that the single robot line coverage problem can be solved in polynomial time with an approximation factor of alpha c plus beta, where alpha c is the approximation factor for asymmetric traveling salesperson problem with c vertices, and beta equals to 2 is the approximation factor for line coverage on rural graphs with a single connected component. Thus, we have alpha c plus 2 approximation algorithm. If the number of connected components in the required graph is very small, that is, if C is an O of log n, then the dynamic programming algorithm gives an optimal asymmetric traveling salesperson problem solution in polynomial time, and the overall approximation factor of the algorithm is 3. In this paper, we describe the line coverage problem for a single robot, wherein the costs for servicing and deadheading are considered to be distinct and asymmetric. We develop approximation algorithms using the minimum cost flow problem, and the development is done in stages based on the structure of the required graph. We show that the algorithm is optimal for the case of Eulerian graphs with only required edges, and it is a two approximation algorithm for graphs with only required edges. Then we discuss the general case of rural graphs with both required and non-required edges. We give an alpha c plus 2 approximation algorithm, where alpha c is the approximation factor for asymmetric traveling salesperson problem with c vertices, and c is the number of connected components in the required graph. Since the asymmetric rural postman problem is a special case of the line coverage problem, our algorithm is also an improvement over the existing results for the asymmetric RPP. Future work includes improvement of the approximation factor of 2 for rural graphs, incorporating turning cost and non-holonomic constraints, online coverage of dynamic environments, and extensions to multiple robots. Thank you.